Thank you very much. First of all, I would like to thank the organizers for the opportunity to give a talk here, and also for the fact that the conference was organized despite all the unfortunate circumstances. So my today's talk is based on a joint work with my student Nelli Abdrahmanova. So the title has been read, and the talk will be structured as follows. First of all, I will give the necessary definitions and describe a general setting. Then I will formulate a rather general problem and say a few words about the history of this problem, and then move to our new results. So the general setting will be as follows. We consider multivariate complex analytic functions, or more precisely, their germs. So we are only interested in the function's behavior in the neighborhood of the origin. All our functions will vanish at the origin. And we assume that there is a finite abelian group G that acts on both Cn and C. Due to Bochner's linearization theorem, we know that these actions can be linearized in a suitable coordinate system, at least locally. So we can think of them just as of linear representations of the group. Moreover, these representations can be diagonalized, so they can be represented as direct sums of one-dimensional representations. Now, a function germ f will be called equivariant with respect to the given pair of the group actions if the following condition is satisfied. So you can first apply a group element and then the function f, or you can do vice versa. You can first apply the function f to a point in Cn and then act on the result by the same group element. So if you always get the same result, then the function is called equivariant. So the only difference here is that in the left-hand side, you have the action in Cn, and in the right-hand side, you have the action in C. And a similar definition can be given for automorphism germs of Cn0, but in this case, both actions are in the same space. Therefore, we have a natural equivalence relation between equivariant function germs. So two equivariant function germs are equivariant right equivalent if there is an equivariant automorphism germ that transforms f into G. So that's a very natural notion. I'd like to say that I will often use words functions or automorphisms without pronouncing the word germ, but in fact, I will always talk about germs here. Okay, so here are two very simple examples. First of all, if we have the group of two elements and its generator multiplies all coordinates on the preimage and on the image by -1, then equivariant function germs are precisely odd function germs. And for example, if we had plus here instead of minus, then we would get even function germs. So invariant function germs would be even function germs. And an obvious generalization of this example, if we take the cyclic group of n elements and its generator sigma multiplies all coordinates on the preimage and on the image by the same primitive nth order root of unity, then equivariant function germs would be given by certain power series in the neighborhood of the origin. And these power series would only include monomials with degrees having residue 1 modulo m. So, this is a generalization of the previous example. Okay, so now we have a space of equivariant function germs with respect to certain representations of the group. And this space is split into orbits of the automorphism group action. So equivariant automorphisms act on the space of equivariant functions, and therefore the space is split into orbits. So an orbit is basically the set of functions that can be obtained from the original function by equivariant coordinate changes. Let us study the behavior of these orbits. Well, in order to introduce some topology in the space, we should also consider finite dimensional subspaces in the space of functions, and these finite dimensional subspaces are subspaces of jets. So instead of considering the whole function germ given by a power series, we can consider its truncated version. We can only take a finite part of the power series and get a certain jet of our germ. So these jets form finite dimensional spaces, basically spaces of polynomials. And these finite dimensional spaces are also split into orbits, but with a very natural topology. So there can be two different cases. Sometimes it can happen that never mind how slightly you perturb your original function, how slightly you perturb the coefficients of this function, you can still obtain infinitely many other functions that are not equivalent to each other. On the other hand, it can happen that if you take a sufficiently small neighborhood of a function, so if you perturb its coefficients very slightly, you can only get a finite number of other non-equivalent functions. And the number of these other functions usually depends on the space of jets in which you work. So our function germ will be called equivariant simple if, first of all, you have a sufficiently small neighborhood of this germ that intersects only a finite number of other orbits. So this means that if you perturb slightly the coefficients of your germ, then you can obtain only a finite number of other non-equivalent function germs. And moreover, the number of these other function germs should be bounded. So it should not increase infinitely as the length of jets tends to infinity. So let me give you a couple of very simple examples so that you get the feeling of what's going on. In these examples, I take functions in one variable, the cyclic group of m elements, and the generator of this group multiplies coordinates on the pre-image and on the image by the same primitive mth order root of unity. First of all, let us consider a germ represented by an equivariant monomial, z to the power mk plus 1. So it is, of course, equivariant, and the adjacent orbits are also orbits of monomial germs, but with lower degrees. So why are they adjacent to the original one? Because you can take the original germ and add here one of these lower degree terms with a small coefficient. Then you can perform a suitable coordinate change, and reduce the whole thing to one of these monomial germs of lower degree. On the other hand, if you add terms of higher degrees, you can still eliminate them by a suitable coordinate change, so they do not influence the orbit. So therefore, the number of adjacent orbits is bounded. It's bounded by the degree of the original germ, and therefore our monomial germ is equivariant simple. So basically, the only not simple example for the case of functions in one variable is the function that is identically zero. In each space of jets, it also has a finite number of adjacent orbits. So they are again the orbits of monomial germs, but the number of these orbits becomes infinite as the length of jets increases. So this is why the identically zero germ is not equivariant simple. So these two examples describe the situation for functions in one variable. This is more or less trivial. And so it is interesting to study functions in more than one variable. The general problem setting would be as follows. To classify up to equivariant right equivalence germs of holomorphic functions from Cn0 to C0 that are equivariant simple with respect to a certain pair of linear representations of a finite abelian group G on the source and target. I also add the condition here that our functions should have a critical point 0. Why? Because if a function does not have a critical point at the origin, then it has a non-trivial linear part. And therefore, by a suitable coordinate change, you can always reduce the whole function to the linear part, or even to a linear function in one variable. So this is not interesting, this is trivial. And that is why we add this condition in hope to get some non-trivial results there. So the problem is very general. I actually have no idea whether one could give a general answer to this problem in this very general form, but there are certain cases where the answer is no. And well, let me show you some of these cases. The very first one historically is the case where there is no group action at all. A very famous result by Vladimir Arnold. And this is the classification of simple singularities in the non-equivariant case. So there are two infinite sequences, AK and DK, and three exclusive cases, E6, E7, and E8. It is worth mentioning that the answer does not really depend on the number of variables. Well, it does depend on the number of variables, but the number of variables only influences the number of variables in the quadratic form that we had here. Then Arnold also studied the following problem that is related to simple boundary singularities. So in our setting, consider the group of two elements whose generator acts on the first coordinate in Cn. So we basically consider functions that are odd, that are even in the first coordinate. And here is the classification of simple singularities in this setting. So aside from, again, AK, DK, and E6, E7, E8, we get two more infinite sequences, BK and CK, and also one more exotic case, F4. So again, the answer does not really depend on the number of variables. A very recent generalization of this result has been obtained just this year by Sabir Hussein-Zadeh, my supervisor, and his student Anna Maria Rauch. They considered a more general situation. They take a certain power of the group of two elements whose generators add certain coordinates in Cm plus n. So basically, they consider functions that are even in each of the first m coordinates. And the result is as follows. So any holomorphic function germ here should be from Cm plus n to C with a critical point 0 again in Cn plus m. That is invariant simple, is actually equivalent to one of the simple boundary singularities obtained by Arnold. So it's again more or less the same list up to a certain permutation of the variables. Okay, so one more result here again has to do with the group of two elements. And here we consider odd functions. So the generator of the group acts on the Cn and on C, multiplying all coordinates by -1 simultaneously. And if we classify odd simple singularities, then here the classification essentially depends on the number of variables. So for one variable, the result is predictable. For two variables, we get a certain non-trivial result, so an infinite sequence and three special cases. And when the number of variables is 3 or higher, then we do not have any odd simple singularities at all. This happens due to certain dimensional reasoning, well, basically because the space of 3 jets of functions in 3 or more variables has a higher dimension than the dimension of the group that acts on this space and influences the jets by coordinate changes. So this is why there can be no simple singularities. Okay, now the next thing that was studied was another cyclic group, Z3, and also there were certain results for cyclic groups of arbitrary finite order. I will just briefly show the results by myself. I'll also present these results at this conference, but 2 or 4 years ago. So here are some results for a general cyclic group with a scalar action. There are certain cases when there are no equivalent simple singularities, and there are certain cases when equivalent simple singularities form one infinite sequence. And I also classified equivalent simple singularities with respect to the group of 3 elements for the cases of 2 or 3 variables. So again, I just briefly show you the results in order to move to our most recent results. So our most recent results deal with the following setting. So we also consider the nth power of the group of 2 elements that acts on Cn and C as follows. So basically, equivariant functions here are functions that are odd in each of the first p coordinates and are even in the remaining n minus p coordinates. So we call such functions odd even functions, and want to classify their simple singularities. The question is, what equivalence relations should we consider here? Because, well, of course, there is the equivariant right equivalence once again, so we can consider equivariant coordinate change which preserve the property of a function to be odd even. But there are also other coordinate changes which preserve this property, but are not equivalent. For example, if you have a function that is even in each of two coordinates, and then you permute these two coordinates, then you again get a function that is even in each of the two coordinates, but the transformation is not equivalent. So we decided to consider a wider class of automorphisms, more precisely the class of parity preserving automorphism germs. So these are the automorphisms that preserve the property of a function being odd even. And how many of such automorphisms are there? So the answer is here. Basically, in order to perform a parity preserving automorphism of Cn, you should take an equivariant automorphism, and then you can also permute coordinates in the function, but you can permute the first p coordinates separately and the last n minus p coordinates separately. So this is the difference between parity preserving automorphisms and just equivariant automorphisms. So we can introduce a weaker equivalence relation on the set of odd even function germs, and therefore get a different notion of simple singularities. And now the classification result is here. So given the group representations, we can say that all simple function germs here are of this form. So we have, first of all, this monomial x1, etc., xp. For instance, if p equals 0, if our functions are even in each coordinates, then we do not have this monomial, then it just equals 1. And then we multiply this monomial by a certain function that is even in each variable. So the functions here and here in these two cases are a little bit different, because in the first case, we have the first coordinate to the power 2k. So it is one of the coordinates in which the function should be odd. And in the second case, we have xp plus 1 to the power 2k. So this is one of the coordinates in which the function should be even. So these two cases are not equivalent even up to the allowed coordinate changes and coordinate permutations. So this is the result. And talking about some further perspective, I think it would be of interest to take, let's say, a group z2 to the power n, but consider the space C n plus n. So a space of higher dimension. such that the group only acts on certain coordinates on this space. We actually started certain work in this direction, and we hope to obtain some results even this year. So to finish, I will show certain references. So the new result, this last new result, will be published this year, also in the proceedings of the SUSDA conference, but of the SUSDA conference from 2 years ago. So that's all I have to say for today, and thank you for your attention.
Thank you very much for the nice talk. Any questions, comments, please?